Thank you very much. Good afternoon. I will present our joint work with my wife, my colleague Miriam Kristekova, and my colleague Peter Moco. Okay, this next. So I will start with motivation, then I will introduce the methodology of our FISP methodology, and then I will show a few applications, and I will finalize with conclusions. So what's the method? Why we are doing this? We know that on-site inspection team seeks cavities hundreds of meters underground, and we know that there is limited time for inspection, limited numbers of seismic stations, and limited possibilities to deploy a large and dense array. Therefore, it's useful to have a robust method utilizing seismic ambient noise applicable to data from single station or few stations measurements. So first of all, let's have a look how the model looks like, what we are seeking. We are seeking cavities, but not like this like on this picture, because we are seeking cavities after underground explosion. And the true model is something like this. On the left-hand side, we see the cavity without chimney, if we are in the plastic rock or if we are in a few seconds and minutes after explosion, and we see cavity surrounded by crushed zone and some under zone of inelastic deformation. In non-plastic rocks, in elastic rocks, usually after a few minutes, up to several hours, there is build-up chimney with the rubble zone, and we have something like we see on the right-hand side. So this is the true model. So this is what we are seeking by our methodology. We performed numerical simulations for these models for several kinds of surrounding structure with alluvial, with granite, and with different filling of cavity. And here we see example of amplitude Fourier spectra for plane wave excitation, and we see three components. And what we see here, we see that we have many spectral peaks on many frequencies, and it's hard to say how to define which is more important, which one is less important. So therefore, we try to find the methodology, and we call this methodology finite interval spectral power. And it's based on that we, instead of problematic identification of individual weak peaks, trying to calculate a corresponding spectral characteristics based on evaluation of signal energy. It means spectral power within a finite interval of frequencies. So mathematically speaking, we are trying to find some integrals, some sum from the interval of minimum to maximum frequency, and we are integrate the smoothed power spectra, either for vertical component or for horizontal components, or, which is very useful, also the ratio of horizontal to vertical components. The question is how to evaluate the power spectral density. The usual method for power spectral density is Welch method, that we divide our time data to small segments, time segments, and we evaluate the spectra, and then we have some statistics. And instead of making some averaging, we are using the kernel density estimate in order to obtain the power spectral density. What does it mean, kernel density estimate? So from our data set, we obtain pictures like this when we see the maximum of the kernel, and we can then assign the power spectral density to the ridge values. And I will not go into details, but this also allows us to evaluate the uncertainty based on the coefficient of variation, and from the coefficient of variation we can evaluate so-called signal-to-noise ratio. And in fact, the larger the signal-to-noise ratio is, this means that we have smaller differences between each segment. So this means that we have more reliable measurements. We have more stable noise, let's say. So this is some evaluation of uncertainty. So, and what we need for the finite interval spectral power method, we need a set of measurements on the free surface about a suspected cavity. It's good to cover the whole area with the seismometers. There is not necessary to deploy all seismometers at once. We can do it step by step and sequentially. And we need sufficiently long 3-component records of seismic noise at all measurement points. What is sufficiently long? It depends on the data, or the quality of data, quality of the noise. We could have a few tens of minutes up to hours. Now I will go to application. I will show 4 applications of our FISP method. The first one was the data on which we developed this FISP method. The data was from Hungary about Great Cavern. The Great Cavern is a roughly oval-shaped cavern with horizontal span about 28 to 30 meters and height about 28 meters, and the depth of sealing was in 70-meter depth. The next one was Tiny Tot. That was a former nuclear explosion with the yield about 20 kiloton in Nevada National Security Site. We don't know the horizontal span and the height of this cavity, but we know that the depth of the cavity was roughly in 100 meters depth. The third one was Rotmos area in Austria. This is the karst area. There is a lot of caves, a lot of deep and shallow caves from depth to 60 to 140 to 450 meters. And we had two profiles there. And the last data was from from the area above the Channel Tunnel in UK. So we know that Channel Tunnel has 2 tubes, 30 meters apart. That at that position, the depth of the Channel Tunnel was around 90 meters. So for the Great Cavern, we obtained roughly 50 measurement points. In this, on the left-hand side, you see the position of the points and 3-component record of noise. And on the right-hand side, you see our FISP values. Here in the picture, you see the horizontal to vertical ratio of FISP computed for the frequency interval from 5.5 to 30 hertz. And what we found out that the anomaly in these FISP maps can somehow show the position of the cavity. And really the red arrow points to the place where the cavity should be. So we see the anomaly is there. The next site was Tiny Tot in Nevada. There were 2 experiments, source physics experiment 5 and 6, and one profile of receivers they used goes straight above this Tiny Tot cavity. So we tried to use those data. That was around 20 receivers, but unfortunately, not all data was possible to use because of some malfunction or interference. In fact, those experiments were not primarily designed for the noise measurements. They were designed for source physics experiments, so for strong motion data. So we were lucky that we found a few days of useful noise, and we can use this. So when we try to evaluate the FISP values, so because the data was not so good, so we played with various FISP parameters, with various length of the data, and you can see here four different lines depicting the FISP horizontal to vertical component, and you see that there is clear anomaly above the Tiny Tot position. So it also corresponds to the Tiny Tot. Now I will move to the two last sites. The first one is Rotmos in Austria. This is the karst area. We had two profiles. You see profile 1 and profile 2, and you see there are depicted position of the caves from 65 meters until up to 450 meters. And this was much more complicated because this is karstic area. So here we evaluated on the bottom. You see our FISP values. With again horizontal to vertical components of FISP, and we are comparing this with 2 other or 3 other techniques. On the left-hand side, on the top we have electromagnetic resistivity method, and in the middle we have active seismic method with MASW method, and on the right this is good for shallow cavities, and on the right-hand side you see on the top, you see the active seismic reflection method, and we can identify. You can go to see the results in the poster. You can download the poster because the poster session was already done. But you can download the poster of Emilia, where this is summarized. And yes, we can see that 4 different frequencies of FISP computed in different frequency range, we can see some patterns corresponding what we see on the other methods. And the last was the channel tunnel. And in this channel tunnel, we again have these FISP horizontal to vertical values. And on the bottom, we have active seismic and reflection tomography. And we can see that in the frequency range from 4 up to 17 hertz, we can see some anomaly in FISP, which could correspond the same with what we see in active seismic. But this is not only on this. We cannot judge whether we can see or we cannot see the tunnel. But yes, there is something. So therefore, it's necessary to use other techniques to prove or to see something like this. So I will conclude that the application of FISP at various locations has shown that the method has potential to identify and locate underground cavities. And yeah, we have many recommendations. I will not go through all of these. You can download that. Okay, for example, you should have sufficiently sensitive recordings. You have to use the most similar conditions possible. You have to disturb as little as possible, so including stuff, so there are noise measurements, and what is most important, you have to subject the obtained results to the sensitivity analysis. You have to play with the data in order to be sure that what you see is really what there is. And finally, I would like to thank to the CTBTO team experts who performed the measurements at all sites and the members of the CTBTO expert group for the fruitful discussions. And thank you. Don't forget to look at the poster.
Thank you. The floor is open for some questions. Put my glasses on. Any questions now, or we can keep them till later? I have one question whilst you're thinking. And maybe it's to you, Joseph, but also to some of my colleagues in the audience as well. How close are we to implementing this during the next integrated field exercise, do you think?
So from our point of view, as a methodology developer, methodology is already done. So now we are thinking how to make it useful for you, for the OSI, and yeah, how far is from your side, it depends on.
Thank you for that. And if we don't have any more questions, we will come back at the end of the session. So for our online participants and you here in the audience, if you do have any questions, we'll come back to them at the end. So thank you for now. Thank you.
Thank you.